Check, check, 1, 2. Good morning, good afternoon, good evening. If it is the middle of the night, you should go to sleep. We're back. We are back. I will be continuing the contribution. I'll be working on LLaVA as usual. And I did want to take the stream, kind of take my time with the stream and really go through the paper diligently. I didn't have too much time to do it off stream, and so I would like to do it on stream and maybe see how it goes in a more loose manner as opposed to a presentation. I think that could actually be very interesting and kind of fun. So let's get it going. I seem to be online. Everything seems to be okay. Let's get. All right, so let's get the paper. So you're going live? Yes, I am. Yes, I am. How's the sound? Is everything coming through okay? How's my voice compared to the music? Yep. Okay, I'll take that as a not overwhelming. Okay, perfect. Good volume. Nice volume, bro. I usually like to peek over the urinal and say that as well. Nice volume. That's a nice ass volume. God damn. Alright, so usually when I'm going through a paper that I've really never read before, it's really important to break these things down into really a few categories. I don't know how many off the top of my head, so we'll just say a few for now. So the first is obviously the algorithm. What are the novelties? Okay. And then obviously we want to know the training data. As well as the evaluation data. As well as, training paradigm. And then evaluation metrics. Evaluate. So if we know the algorithm, what the main proposition is, what they trained it on, how they trained it, what they evaluated it on, and then how they evaluate it, we have a pretty good understanding of how to of this paper itself. And so really from there we can begin. Usually what I have tried earlier, sorry about that. What I've tried earlier is if you go through earlier videos of mine, I'll just kind of read through the entire paper. But realistically, none of us are actually going through the paper like that. We kind of segment it into chunks that we find to be, that we try to understand it in. So it actually won't be in order. The introduction is just a lot of whatever. It kind of sets the tone, gives some context, but even then, it's really not that. It's really not that important if you already have a good prior understanding of where this model is coming from, where the researchers are coming from. So really, when it comes down to it, what we will start with is reading the abstract and the conclusion first. Okay. Now, why read the abstract and conclusion first? Well, this isn't even my idea. This has been Andrew Ng, who is, I mean, it's Andrew frickin' Ng, you know, like if you're in machine learning, you know this guy. Absolute legend in teaching, absolute legend in just in the field in general. A lot of what I'm going to be saying comes from him. So, you know, starting with the abstract and conclusion first. Actually, this gives you an idea of especially number one, but also a bit of number two as well. So this kind of tells us, everything in a short and sweet manner. Short and sweet. So let's do that, and then what we will do is actually go so abstract and conclusion, and then what's section 3? I think this looks like this does look like some more context. And then 4, here we go into the architecture, we go into the training, experiments. What else? And this is all the experiments as well, still continuing the experiments, and conclusion. Okay. So we see now, kind of, once we're done with the abstract and conclusion, where to jump to, pretty much, which is going to be section 4 and 5, because section 6 will be the conclusion. And then once we have a good understanding of, so in this case, I'm just gonna write section 4 and 5. And then once we really have a good understanding of that, we can go to section 1 and 2. Conclusion, as we know in this paper, is section 6. What I would say in this case is that section 1 and 2 is obviously useful. I mean, the authors spent time to write that part. But I would definitely focus on this, especially if you are doing active research in what this paper is proposing, or what any paper is proposing. Otherwise, it just gives nice context. Now, I'm not an active researcher in multimodal language models, or multimodal models in general, but this will still be nice for me to have in the back burner of my thought process. Okay. Sorry, I messed up the volume here. One sec. Okay, so let's just start with the abstract and conclusion. So, instruction tuning large language models using machine-generated instruction following data has been shown to improve the zero-shot capabilities on new tasks. But the idea is less explored in the multimodal field. We present the first attempt to use language-only GPT-4 to generate multimodal language, image, instruction following data. So let me write this down real quick. Obviously, taking active notes is always the best way to read anything. So we present the first attempt to use language-only GPT-4 to generate multimodal language image instruction following data. So already what they're proposing here is language only, GPT-4, to give instructions, right? To generate language image instruction. Image instruction data. Now, immediately you may be thinking, okay, well, what is instruction data specifically? What do the researchers mean by instruction data? And specifically, what do the researchers mean by instruction data, and how is it different from just a text corpus? Well, the idea here is that for instruction data, this is going to be heavily back and forth. There's going to be a back and forth conversation here. So instruction data is you going in, and in this context, you have vision, it's language and vision. You may give it an image and prompt it. Let's say it's an image of some concept art, and then you give it an instruction. You say, hey, give me a name and background for this character in this book that I'm writing. And then the idea is that it will feed in both the image and the language instruction here into the language model, and then you will get the output. So you feed it with the instruction and the image, and based off of both the image and the text input, you get a text output from the model. So this is what we mean by instruction data. Now, there are various paradigms to train this, and we'll see what they discuss here. So we present, so by instruction tuning on such generated data, we introduce LLaVA, Large Language and Vision Assistant, an end-to-end trained large multimodal model that connects a vision encoder and an LLM for general purpose visual and language understanding. To facilitate future research on visual instruction following, we construct 2 evaluation benchmarks with diverse and challenging application-oriented tasks. Okay, cool. So already, if we want to make a little box here for novelties, not only is it going to be the network itself, but also 2 eval benchmarks. Cool. Let's highlight it too. Looks cool. Boom, novelties. Boom. Okay. Our experiments show that LLaVA demonstrates impressive multimodal chat abilities, sometimes exhibiting the behaviors of multimodal GPT-4 on unseen images and instructions, and yields an 85.1% relative score when compared to GPT-4 on a synthetic multimodal instruction following dataset. When fine-tuned on Science QA, the synergy of LLaVA and GPT-4 achieves a new state-of-the-art accuracy of 92.53%. We make GPT-4 generated visual instruction tuning data, our model and code publicly available. Always a good thing. Always a good thing. Always a good thing. Okay. My nose is so stuffy right now. Oh my god. I'm at that point right now where I can't breathe, but I can. It's so weird. I take the wrong breath and I get stuffed. Oh my god. Okay, I didn't want to subject you to my unnecessary inhales. All right, so now that we've read the abstract and we have a bit of an idea of what they're proposing. Let's just jump to the conclusion. All right. All right. So this paper demonstrated the effectiveness of visual instruction tuning. We presented an automatic pipeline to create language, image, instruction following data. Okay. Again, this is why I'm not trying to print anything. So they present automatic pipeline to create language image pairs. Okay. Based on which we train LLaVA, a multimodal model, to follow human intent to complete visual tasks. It achieves the new state-of-the-art accuracy when fine-tuned on Science QA, and excellent visual chat capabilities when fine-tuned on multimodal chat data. Besides, we present the first benchmark to study multimodal instruction following capabilities. This paper is an initial step in visual instruction tuning and mainly focuses on real-life tasks. For more quantitative results of LLaVA on academic benchmarks, please refer to the improved baselines with visual instruction tuning. We hope our work can inspire future research. Okay. All right. Oh wait, what I just do? So now we know, kind of at this high level, what's going on. So now let's jump to the actual proposition itself. All right. Well, oh, so actually what I'm going to do is, so I did skip, I'm going to say 3 and 4 and 5. So I thought that this was more context. But now that we've read the abstract and conclusion and know what they're going to propose, actually 3 is important for this the proposition itself. So related work we can go about later if needed. So GPT assisted visual instruction data generation. So this was something that they proposed. Ooh, look at that, look at that, look at that, look at that, bro. Look at that. Okay, so let's... Hello? All right, cool. So let's see how we can get the GPT assisted visual instruction data generation. So this community has witnessed a surge in the amount of public multimodal data, such as image text pairs ranging from CC to Lion. However, when it comes to multimodal instruction following data, the available amount is limited, partially because of the process for creating such data is time consuming and less well defined when human crowdsourcing is considered. Now, before I continue, let's look at this table because this gives a good idea of what is required for this image language instruction following model. So, table 1. One example to illustrate the instruction following data. The top block shows the context, such as captions and boxes to prompt GPT, and the bottom block shows the 3 types of responses. Note that the visual image is not used to prompt GPT, we only show it here as a reference. Okay, I see. A group of people standing around a black vehicle with various luggage. Luggage surrounds a vehicle in an underground parking area. People try to fit their luggage in an SUV. Let's zoom in here and see what this is about. What's going on? I agree with this caption. Okay. Some people with luggage near a van, near a van that is transporting it. Okay, context 2, type 2 boxes. person. Okay, I don't know what context 2 is. So what is this? Person, 0.681.2427. Backpack, suitcase, amended. So is this, so boxes, I guess they'll discuss this in later. So I guess they use, it seems like they're using something like a segmentation, like a, oh my god, what's that? Like a YOLO V8, V whatever, V1 million. They pump out a new YOLO every year at this point. Yeah, so whatever YOLO model, for example, to get these bounded boxes. And then it looks like we have the according labels from it. Seems like we'll read this more, but that's just my guess. Response 1, type 1 conversation. Question: what type of vehicle is featured in the image? The image features a black sporty utility vehicle, SUV. Black vehicle, SUV. So again, GPT isn't, it doesn't see this image, right? So it's just based off of these contexts, is generating these responses. Response type 2, detailed description. The image is an underground parking area with a black sporty utility vehicle, SUV, parked. There are 3 people in the scene. 1, 2, 3, and then maybe because this is uncertain, maybe this isn't a high enough value. Well, then by that token, it'd be 1, 2 backpacks, surrounded by various pieces of luggage, including suitcases and backpacks. Oh, okay, because this is omitted. I see. They are facing the challenge of fitting all their luggage into the black SUV, which was mentioned. There are multiple suitcases and backpacks to be packed, which suggests that the group has a significant amount of belongings, blah, 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 blah. Okay. Oh, wait. No, this is, oh, I see. I'm reading the wrong thing. There are 3 people in the scene, with 1 person standing closer to the left side of the vehicle, another person in the middle, and a 3rd person to the right side. Is this even true? 1 person standing closer to the left side, 1 person in the middle, the 3rd person on the right. I mean, not really. They're all working together to pack the SUV for a trip. And then what challenges do they face? They're surrounded by, okay. This is interesting. I feel as though there's just so many hallucinations that could come about this. So I am confused as to how they mitigate something like this. Because I feel like without showing the image reference, we have with 1 person standing closer to the left side of the vehicle, another in the middle, 3rd on the right. I mean, technically they're both on the right. I'm sure GPT-4V might be able to discern that this is the left side of the vehicle. I've actually never really fully played around with it, so I can't say for sure. Okay. All right, so inspired by the success of recent GPT models in text annotation tasks, we propose to leverage ChatGPT GPT-4 for multimodal instruction following data collection based on the widely existing image pair data. For an image and its associated caption, it is natural to create a set of questions with the intent to instruct the assistant to describe the image content. We prompt GPT-4 to curate such a list of questions, details later. Therefore, a simple way to expand image text pair to its instruction following version is human question value stop assistant caption stop. So cheap to construct the simple. Wait, what? So we say that the human asks the question. Asks, it's a set of questions, and then what's, as well as the image stop, and then the assistant responds with the caption. Oh, I see. So we have, I see what this means now. Okay, this took me a second. So we have, and I hope I'm understanding this correctly, but I think I am. We have the image, and we have the caption related to the image already. What they propose is simply to construct the set of questions based off of these pairs that we already have, such that when we train the model, we can feed in the questions and feed in the images, because this will be the multimodal model. This won't just be the language model. But we could feed this in hopes that it gets close to the output being the caption. I think this is what they do. Though cheap to construct, the simple expanded version lacks diversity and in-depth reasoning about the instructions and the responses. Okay, so it seems like, okay. This is the simple way to do something like that. Okay. To mitigate this issue, we leverage language-only GPT-4. ChatGPT is the strong teacher. Both accept only text as input. To create instruction following data involving visual content. Specifically, in order to encode an image to its visual features, to prompt a text-only GPT, we use two types of symbolic representations, which is captions and bounding boxes, usually to localize the objects in the scene, which we see here. So we feed in the captions and then the bounding boxes. Where were we? Each box encodes the object concept in its spatial location. One example is the top block of table 14. All right, so this is the full thing. All right, so we have all this. Okay, cool. Let's go back. The symbolic representation allows us to encode the image as LLM recognizable sequence text. We use Cocoa images and generate three types of Cocoa images? Common objects in context. Okay. And generate three types of instruction following data. One example per type is shown in the bottom block of table 14. So table 14 is just an expanded version of this, and it's just these three reasoning types essentially, but it's not omitted. For each type, we first manually design a few examples. They are the only human annotations we have during data collection and are used as seed examples in context learning to query GPT-4. And so the three tasks are conversation, detailed description, and complex reasoning. Okay. We collect 158,000 unique language image instruction following samples in total, including 58,000 in conversations, 23,000 in detailed description, and 77,000 in complex reasoning, respectively. We ablated the use of ChatGPT and GPT-4 in our early experiments and found that GPT-4 consistently provides higher quality instruction following data, such as spatial reasoning. Okay, so that's cool. So now we know, if we go back here, now we know. Come on, brother, please let me highlight. All right, now we know how they generated this pipeline. Cool. Now let's get to the model itself. So now we've generated all this data, and we are reasonably confident in the three types of data, three types of assistance we want. So now we have to design a model. Now that we have the images, we have the questions, and we have the necessary answers for these images. We can actually train all of this jointly. Really, that's the whole goal of this, right? Prior to this, we didn't have this multimodal assistant. We figured out a convenient way to generate all of this data. And so now we can train a multimodal model with this data. Cool. So let's talk about the architecture itself. The primary goal is to effectively leverage the capabilities of both the pre-trained LLM and visual model. The network architecture is illustrated here in this figure. We choose Vicuna as our LLM, parameterized by phi, as it has the best instruction following capabilities and language tasks among publicly available checkpoints. And then, as we can see here, we have our image that's fed into a vision encoder, projected, and then we get HV, which are the embeddings. The vision embeddings, the image embeddings, and then we have the language instruction, the text, the query or the question, and then that's just directly embedded. And then now we have these embeddings jointly that are fed into the language model to get the language response. So let's see. I'm interested in how they concatenate these two embeddings together. So let's see. For an input image, we consider the pre-trained clip visual encoder, which provides the visual features Z of V. The grid features before and after the last transformer layer are considered in our experiments. The grid features before and after. I don't know what this means. Let's see if this paper mentions anything about grid features. Is this the grid here? Yeah, I don't know what this means, in all honesty. We consider a simple linear layer to connect image features into word embedding space. Specifically, we apply the projection W to convert ZV into language embedding tokens HV, which have the same dimensionality as the word embedding space in the language model. So these will be the same dimensionality. Thus, we have a sequence of visual tokens HV. Note our simple projection scheme is lightweight, which allows us to iterate data-centric experiments quickly. More sophisticated schemes to connect the image and language representations can also be considered, such as gated cross-attention in Flamingo, Q-former, and Blip2. We leave exploring possibly more effective, sophisticated architecture designs for LLaVA as future work. But as of now, it seems like it is just a simple linear projection. Okay, now let's see how we train. For each image x of v, we generate multi-turn conversation data. The first question, first answer, t number question, t number answer, where t is the total number of turns. We organize them as a sequence by treating all answers as the assistant's response and the instruction x instruct t as the tth turn as. So the instruction is, so if the first turn, so if we're on the first turn, we randomly choose between, so hold on. We organize them as a sequence, okay? So if it's the first turn, we randomly choose either the first question and the image, or the image and the first question. Otherwise, we just get the T index question. I'm not fully sure what the difference is between the order is of the sequence here. This leads to a unified format for the multimodal instruction following sequence illustrated in Table 2. We perform instruction tuning of the LLM on the prediction tokens by using its original autoregressive training objective. Okay. Specifically, for a sequence of length L, we compute the probability of the target answers XA by, let's see, probability of X of A given the image and the instruction is the, we multiply all the probabilities of X sub I given the image, given the instruction, less than I, and given the answer less than I. Oh, so this is just the this is just kind of that. Is this the autoregressive aspect of it? So we're just taking all the probabilities to everything before it, right? That's what, hence the less than I. We don't want to consider the probabilities of subsequent tokens. I assume X of I is a token here. Current prediction token. Yes. Okay. This is fine. This isn't crazy or new. Table 2, the input sequence used to train a model. Oh, okay, this is cool. Only 2 conversation turns are illustrated here. In practice, it varies. Okay, so let's see. System message, stop. Human gives the first instruction, stop the assistant. Green is used to compute the loss in the autoregressive. Okay. So we stop, and then the assistant tries to predict the first answer, stop. And then we have a second instruction, and then the assistant tries to predict the second answer. Theta is the tradable parameters. Instruct I and XAI are the instruction and answer tokens before the current prediction. Yes. Okay. So my assessment was correct on this. Please see table 2 for the illustration. For the conditionals in equation 3, we explicitly add the image to emphasize the fact that the image is grounded for all the answers. We omit the system message and all previous stop for better readability. For LLaVA model training, we consider a two-stage instruction tuning procedure. So I do like that. So the image is given such that there is some grounding, there is some anchor. There's some grounding mechanism for the token prediction here. Pre-training for feature alignment. So this is the 2-stage instruction tuning procedure. Am I blurry? Cool. All right, so first we pre-train for feature alignment. Strike a balance between concept coverage and training efficiency. We filter CC3M to 595,000 image text pairs. Please see appendix for details of the filtering process. These pairs are converted to the instruction following data using the naive expansion method described in section 3. Each sample can be treated as a single turn conversation. To instruct the input for each image and a question is randomly sampled, which is a language instruction to request the assistant to describe the image briefly. The ground truth prediction is the answer. The ground truth is the original caption. So it's this paradigm here that they said that is not a star. it's this here that they it seems like they use as pre-training. In training, we keep both the visual encoder and LLM weights frozen and maximize the likelihood of equation 3 with the trainable parameters theta equal W, the projection matrix. In this way, the image features can be aligned. I see. So we this is very interesting. I see. So what they do here is they first had a problem with generating data, and they said, well, we could do this kind of really simple and naive method. Sorry, let's go back to where we were. We have this naive method, which I'm going to assume that they tried and thought was a good first step, and then kind of saw the failures in this. But clearly it wasn't a failure, because this naive method ends up being very useful to train this projection matrix. So if you have the architecture and you do this naive method of generating questions, the image, and then the cap and the necessary answers, you freeze everything except for your projection matrix, and essentially train only your projection matrix, then actually you have a very meaningful this naive method actually allows for a very meaningful vision encoder to image embedding projection matrix. That's very cool. That's very neat. This way, the image features can be aligned with the pre-trained LLM word embedding. Yes. This stage can be understood as training a compatible visual tokenizer for the frozen LLM. Which, yeah, it is. Fine-tuning end-to-end. We always keep the visual encoder weights frozen and continue to update both the pre-trained weights of the projection layer and the LLM in LLaVA, i.e. the trainable parameters, W, theta, A is W phi, the set of W and phi. We consider two specific use case scenarios, a multimodal chatbot and science QA. Okay. So now let's go back up here. We now have a good idea of LLaVA itself and how to train the model. Then let's talk about the experiments, which is probably going to be split into multimodal and there's actually quite a few experiments. Okay. All right, let me just change the music real quick. And what should I play? All right, let's play this. All right, so let's go to the experiments. We assess the performance of LLaVA in an instruction following and visual reasoning capabilities with two primary experimental settings, multimodal chatbot and the science QA dataset respectively. We train all models with 8 A100s following Vicuna's hyperparameters, as defined probably in the Vicuna paper. We train our model on the filtered CC595000 subset for one epoch with a learning rate of 2E-3 and a batch size of 128, and then fine-tune the proposed LLaVA Instruct 158K dataset for 3 epochs with a learning rate of 2E-5 and a batch size of 32. All right. So now for the multimodal chatbot. We develop a chatbot demo to show the image understanding and conversation abilities of LLaVA, and to study how well LLaVA is able to digest visual inputs and exhibit instruction following capabilities. Okay. Demonstrates good Yeah, I mean, is there, yeah, qualitative evaluation? Um, Specifically, we create triplets. So they leverage GPT-4 to measure the quality of generated responses. Specifically, we create triplets consisting of image, ground truth, textual description, and question. The candidate models predict the answers based on the question and image. To provide an approximate theoretical upper bound, we create a reference prediction based on the question, the ground truth textual descriptions using GPT-4. After obtaining the responses from both models, we feed the question visual information and the generated response from both assistants to the judge. It evaluates the helpfulness, relevancy, accuracy, level of detail, and gives an overall scale of 1 to 10. I mean, sure. I'm just. I know that there's a lot of work going on in using LLMs as judges for each other, but I've read a few papers on it, and I don't know. I'm not fully convinced on it. I'm really not. But I mean, this is kind of where we're at right now, so everyone's kind of doing it. So you know, if it ain't broke, don't fix it. But I'm not fully persuaded on using this. And then we have, I assume these are the two evaluation sets that they propose: Lava Bench, Coco, and In the Wild. Yeah, so they take 30 images and then construct. This benchmark studies the model's alignment, behavior, and capabilities with consistent visual inputs. We vary the training data to study the effectiveness on different types of instruction following data and show the results here in table 4. And then in the wild, they collect a diverse set of indoor outdoor scenes, memes, paintings, sketchings, etc. With a highly detailed and manually curated description and proper selection of questions. We compare Lava, Blip, and Open Flamingo. Sure. Okay. Sure. I don't know. I think the evaluation aspect is, it is what it is. I'm again, I'm not, I don't doubt the results. It's just I don't think there's too much else to discuss here. So the evaluation metrics in this case will be using GPT-4 as a judge, and then they develop these two, and then it seems here that in the wild dev set, they have a lot of details to really probe at multimodal models. So let's see the science QA. It contains 21,000 multiple choice questions with rich domain diversity across 3 subjects, 26 topics, 127 categories, 379 skills. Okay, we consider 2 representative methods. So the text DaVinci 2, with and without chain of thought, Llama adapter, as well as multimodal chain of thought, which is a current state-of-the-art method on this data set. So let's just jump to this table here. So it seems as though they're doing, is it better than everything else? Average, yeah. So they, oh yes, this is right. So Lava base does quite well, and then when they use GPT-4 as the judge, they're able to bump it up to 92%. Which is what they mentioned in like the conclusion. Okay, cool. So now we have a pretty good idea. We have a pretty solid idea of this model. I feel quite comfortable with this model, and obviously I'm going to be adapting it to Torch multimodal in a bit. I will probably be working on that on Wednesday. I will see you guys then. Thank you for tuning in. Have a good one. Peace.